What's up, guys? Welcome back to another Algebra 2 instruction lesson here with Mr. Gaines as we continue our discussion on one-to-one and inverse functions. Last time we looked at the definition of one-to-one functions, which are going to play a significant role as we progress into our topic for today, which is inverse functions. Now, I'm not going to give you a discovery, but rather go directly into the definition of an inverse function and try to use this diagram to help us to visualize what an inverse function is going to work or to represent. So in order to have an inverse function, the normal or the first requirement is that our original function, let's say f in this case, is 1 to 1. So for a function's inverse to also be a function, we are going to originally start with one-to-one functions. So if you haven't learned about one-to-one functions yet, go ahead and check out the last video where we break down that definition. So an inverse function, and let's see some new notation right here. This notation means inverse. So f to the negative first power of x is not a reciprocal, it's an inverse operation. So this would mean inverse. The inverse of f of x is a one-to-one function with an ordered pair BA. So if I have a b on a function, its inverse is going to flip. The y value now becomes the x value, and the x value now becomes the y value. Essentially what this does is it takes all the values from the domain and the range and switches them. So let's say that here we have the domain of f, and let's say that f and g are inverses. So on this picture, everything represented in this bubble here is the domain of f. It is also the range of g, so it's represented with the value a. So on f, a is an x coordinate, but on g, a is a y coordinate. Vice versa here, this bubble here would be represented as b, which is the range of f, a y value, but the domain of g, an x value. So inverse functions take x values and y values and switch them amongst one another. So let's take a look at that in some application or some practice here. So in problem 4, it says consider the two linear functions given by the formula f of x equals 3x plus 7 over 2 and g of x equals 2x minus 7 over 3. So we see these functions have some similar pieces, but they're not exactly the same. Let's take a look at what happens when we start to evaluate them. So in problem part A, it says to evaluate f of 5. So if I go ahead, we can do this in the calculator. If I substitute 5 into f of x, this would be 3 times 5 plus 7, and all of that would be divided by 2. So f of 5 is 11. And it also says to find g of 11. So g of 11, we could substitute into the calculator as well. G of 11 here would be 2 times 11 minus 7. And that value divided by 3 is 5. So we may notice something there. The x value for f of x matches with the y value for g of x. And vice versa, the y value for g of x matches with the x value of f of x. So the domains and the ranges between these two, the domain and range values shown, are opposites of one another. Now let's go ahead and let's continue this a little bit further. In part B, it says to evaluate f of 0. F of 0, if we could do that in the calculator if we needed to, but this would be 3 times 0 plus 7, which is 7 over 2. Then in g of x, it tells us to evaluate g of 7 over 2. So 2 times 7 over 2 minus 7. And this all divided by 3 would be 0. So again, you might have been able to get to this without actually typing into the calculator. But again, we see the x value from f is the y value on g. Conversely, the y value from f is the x value from g. So these appear to be two inverses of one another. Now, we only show that that works through two sets of points on the functions. So this doesn't necessarily, it's not a proof, but it lets us to see some examples. Now, let's go ahead and take a look at what might happen if I do a function composition. So in problem C, it says f of g of -1. So in this case, I first want to evaluate what g of -1 would be. So g of -1 would be 2 times -1 minus 7, and that divided by 3. So g of -1 is -3. And then I'd be finding f of -3. So 3 times -3 plus 7 divided by 2 would be -1. So f of g of -1 is -1 here. What do you think f of g of 5 might be? Let's see if your hypothesis would be correct. So first we could evaluate g of 5, which would be 2 times 5 minus 7 divided by 3. So g of 5 is 1. And then we would be wanting to find f of 1 using our function composition here, which would be 3 times 1 plus 7 divided by 2. And hopefully you said f of g of 5 would be 5. You may notice here that these functions are undoing each other's operation. So without calculation, it says determine the value of f of g of pi. Well, if these two functions undo one another, and through the substitution and composition process, we would be left with pi. And you could check that by substituting in that value and seeing that this would remain. So what we can see here is these two functions, they actually are inverses of one another. Now, eventually we're going to get into the proof, how to determine that they are, how to show that they are functions of one another. But for right now, I'm telling you that they're inverses of each other. So what we can see is that the input and the output values in A and B are flip-flopped amongst the two functions. Also, what we can see in C, D, and E is that through function composition, the two inverses undo each other's operations. This is actually the process that we use when we solve linear equations, quadratic equations, any equation that we're trying to solve for a variable x. This is the process that we go through in most cases. We use inverse operations. Now we kind of have a reason behind that. So let's go ahead and take a look at some more examples of what happens with inverse functions. So in problem 5, it says if the point -3, 5 lies on the graph of y equals f of x, then which of the following must lie on its graph of its inverse? So we know that f of x has this point -3, 5, and we want to find the point that would exist on its inverse. Well, remember, again, inverses take the x and the y coordinates and they switch them. So the sign sticks with the coordinates. So this -3 now becomes y, and this 5 now becomes x. So we'd be looking for the point 5, -3. So by definition, that x and y value is going to flip. So the point 5, -3 would exist on f of x's inverse. We don't know about any of the other points. They could, they may not. But we do know that 5, -3 will exist on the inverse because that is the opposite domain and range values that were given to us on the original function. Now let's take a look at 6, and let's go ahead and take a look at some graphing of inverse functions. So it says the linear function f of x equals 2/3 x minus 2, and it's shown here in the graph. Use its graph to answer each of the following questions. Evaluate the inverse of f of 2 and the inverse of f of -4. So let's break this down a little bit. The inverse of f, given an x value, would be the same y value on our original function. So basically what we want to find here, the inverse of f of 2 would be the same as finding the f of x value that leads to a y value of 2. So I can find this on the graph here. This point over here on the right side of the graph, this point would be 6, 2. So what I'm going to do is take a look at the coordinates. So if I want to find the inverse of f of 2, I can look at this coordinate pair, and it's going to be the corresponding x value on the original function, and so it would be 6. See if you can find the inverse of f of -4. So the inverse of f of -4 would correspond to f of x equaling -4. So what we're looking for on the original function is a y value of -4. We can see that point right here. This point would be -3, -4. So the inverse of f of -4 would be -3. So what we're doing again, we've done this with original functions. We've been given an x or a y value and we're finding the opposite. Now what we have to do here is remember that if this is f of x, the inverse would flip the domain with the range. Those values would switch. Now the question in B says determine the y-intercept of the inverse of f of x. Well, if we're looking at the y-intercept of the inverse of f of x, thinking about the definition, this is going to be the the x-intercept on f of x. Any x-intercept would become the y-intercept. So this x-intercept would be 0, sorry, not 0, but 4, 0. Sorry, let me count correctly, 3, 0. So that point is, as we take to the inverse, the x and the y's are going to change locations. So this would become 0, 3 on the inverse of f of x. So the y-intercept is going to be at y equals 0, where the x-intercept on the original function is x equals 3. It becomes, sorry, excuse me, the y-intercept would be y equals 3. So now it says on the same set of axes, draw a graph of the inverse of f of x. Let's go back to the definition. What does the inverse operation do? Well, it takes each of the x coordinates and the y coordinates and it switches those. So let me go ahead and label just a couple remaining points here. 0, -2, and this would be -6, -6. If we want to graph the inverse of this function, we can take all of the points that are listed there and switch the x and y values. So 6, 2 would now become 2, 6. So that point that's in the top right in quadrant 1 right now is now still in quadrant 1, but it's 2, 6. 3, 0 would become 0, 3. 0, -2 would become -2, 0. -3, -4 would become -4, -3. And -6, 6, sorry, -6, -6 would remain -6, -6. And so here we have the graph of our function. Sorry, I plotted one incorrectly. That should be at 0, 3. There we go. So this would be our inverse function. So our inverse function, if you think about in terms of transformations on the graph, you may notice that this inverse function is a reflection about y equals x. So all inverse functions are going to switch the x and the y values, which in turn, transformationally, will be a reflection across y equals x. So this gives us some examples and some explanations of the definition of an inverse function. This is a pretty good place to stop. As we progress, we will start to get into exactly how to prove that these are inverse functions. Thank you guys for tuning in, and as always, I'll see you soon.